Alright, so we are going to look at the derivatives of transcendental functions today. And so your definition of transcendental functions are functions that transcend algebra. They go beyond the operations of addition, subtraction, multiplication, and division. So, for example, a quadratic formula is not transcendental because even though it's got that square, that exponents are really just multiplication. Some examples of transcendental functions are trig functions, exponential functions, logarithmic functions, and etc. We'll see some more later. So, we're going to start with our trig functions. So, to take the derivative of trig functions, there are two things that you need to know. The derivative of sine is cosine, and the derivative of cosine is negative sine. These two are ones that you want to have memorized and memorized well, because we're going to use them a lot. So, for our first example here, we're asked to find the derivative of all of these. Actually, I didn't put directions, but that's what I want you to do. Find the derivative for all of these functions. So, whenever you take the derivative of 2 cosine x, you're just going to get 2 times the derivative of cosine x is negative sine x. That 2 is just a coefficient, so you don't really do anything with that coefficient. It just sort of stays out front. So we would, of course, not leave it like that. We would write this as negative 2 sine x. Notice that I labeled this f prime of x. Anytime you take a derivative, you need to label that it is the derivative. Don't just put an equal sign, because that makes it look like you're still dealing with f of x. Alright, for example 2, this one looks a little bit different. We've got sine x over 2. However, it's really no different than the problem that we just did. Instead of thinking of this as sine x over 2, think of it this way. 1/2 times sine of x. This is equivalent because if you were doing this, if you're going to multiply this back together, this would be sine x over 1. You'd multiply the numerators together, multiply the denominators together, you'd get sine x over 2. So, 1/2 is just a coefficient here. So, the coefficients, whenever we're taking derivatives, we just leave them alone. We've got this 1/2 right here. And the derivative of sine x is cosine x. So we would just have 1/2 cosine x. You might see this written as cosine x over 2 instead. Because again, if you put this cosine x over 1, you can just multiply straight across and you would get cosine x over 2. Okay. Example 3 is our equation here, 2x minus sine x. And so, whenever you take a derivative like this, you have two different types of functions sort of put together here. The derivative of your 2x is just 2. So, you're taking the derivative of it separately from your sine function. And then, the derivative of sine x is cosine x, so we would just have 2 minus cosine x. And that would be our answer for these. A lot of these trig functions are really simple to do. But a lot of students have trouble with them because they don't ever memorize their derivatives of sine and cosine. So here we have an equation. This is actually not transcendental, but I wanted to look at this because it deals with a type of problem that we're going to see and need to know about. So I'm sort of throwing this in here. This is a little bit of a review. And so we have a pumpkin is launched from a height of 15 feet with an initial upward velocity of 60 feet per second. And we're going to use this equation right here. H equals negative 16t squared plus v sub 0t plus h sub 0. That formula may look familiar to you because we used that a lot in Algebra 1 whenever we did our pumpkin chunkin activities. However, you guys did not have me for Algebra 1 because you took it in the 8th grade. So I'm not 100% sure how much Miss Baller or Miss Swisher did with this, but this gives us the height of an object after a given amount of time. So first thing we need to do here is we need to fill in what we know for our equation. So this v sub 0 is our initial upward velocity, so we need to replace that with 60, and this h sub 0 is our initial height, and our initial height here is 15. So the equation we're looking at is h equals negative 16 t squared plus 60 t plus 15. And so that equation will give us the height of the pumpkin after t seconds. And so the first question we have here says, what was the average speed of the pumpkin from 0 to 1? So when we're seeing average speed, we're not thinking instantaneous, but rather the distance divided by the time. We're thinking of like a slope formula here. So I'm going to call this h of t here just because it makes it a little easier for our notation here. So if I do h of 0, the height at 0, then I would get negative 16 times 0 squared plus 60 times 0 plus 15, and I just get 15 for that. So I have the point 0, 15. And then if I plug in 1, if I have h of 1, I would have negative 16 times 1 squared plus 60 times 1 plus 15. And whenever I do that, I'm going to have negative 16 and positive 15 is going to be negative 1 plus 60. I'll get 59 here. So I've got the point 159. And so at 0, my pumpkin was at a height of 15. At 1, my pumpkin was at a height of 59. I want to see the distance over the time. So the distance would be 59 minus 15, which of course would give us 44. And the time would be 1 minus 0, which of course is just 1. So we would have 44 feet per second. Now, this is our average speed, not our instantaneous speed. Now, the instantaneous velocity of the pumpkin at t equals 1. This is going to be the slope of the tangent line right there at 1. If you think of this graph here, if we think of what we've got, we had, here's 15, here's 1, we'll put 49 up here, so we had this point right here and this point right here. Just from what we know this function is quadratic, so it's doing something like this probably. And so what we just found here, our average rate of speed, was the slope between those two endpoints right there. But if we want to know the instantaneous velocity, we need to know the slope of the tangent line. Remember, this is distance in feet, and this is time in seconds. So if we're finding the slope, we're doing feet, changing y, divided by time, changing x right here. And so feet divided by seconds, of course, is our velocity. So the derivative is going to give us this. And now that we know how to find the derivative using the power rule, this is much easier than it was whenever we had to use our limit definition of a derivative. So to find our instantaneous velocity, we can just find h prime of t. We'll just take the derivative of our function. And the derivative of that function is going to be negative 32t plus 60. And if we want to know that instantaneous velocity at 1, we're going to have h prime of 1. Make sure you label this right here and show that you plugged in 1. You've got negative 32 times 1 plus 60. And whenever you do that, you're going to get a 28 feet per second for your answer here. We are asked, what was the velocity of the pumpkin when it hit the ground? So if you think of what's happening here, you've got your pumpkin, it's going up, it's coming back down, it's going to hit the ground right here. And at that point, your y coordinate has to be 0. So that, remember, this is your h and this is your t, so really I guess it's your h coordinate has to be 0. So you're going to say 0 equals negative 16t squared plus 60t plus 15, and you want to solve this equation. You can use quadratic formula, You can use you can really use anything you want. I'm going to show you a trick with the calculator. Okay, so these TI-89 calculators, they're very powerful. That's why we don't want you to use them in the lower grades. So they will solve equations like this for you. So if you click F2, which is algebra up here, you want to solve. So you're going to put solve right here. And so you're going to type in your equation. So 0 equals, I can use a t if I want. I'm just going to use the x because it's just easier to type in. So negative 16x to the second plus 60x plus 15. And then whenever you're solving an equation, if I just put my parentheses here and hit enter, I'll get an error. It says too few arguments. So I'm going to go back. What you have to do after you type in your equation that you're wanting to solve, you have to put a comma and you have to put the variable that you want to solve for. So in this case, since I used the x here, I want to solve for an x. And then you must close your parentheses, because if you don't close your parentheses, then it's not going to allow you to solve this equation. So if I hit enter, it might take it a second. See, I get these two answers, and oh, they are ugly. I could give it as the answer, but it's not going to help me all that much for what I'm wanting to know here. So remember, with these calculators, they simplify your radicals. You would like to have these in Math 3 and Pre-Cal, I'm sure. But if you'll hit the green button and then hit enter, it'll give you decimal approximations. So we've got 3.98524. and then we've got negative 0.235. This is not the x-intercept that we want because it doesn't make sense for our situation. We want this answer right here. X equals, let's see what that was again, 3.9524. 3.95, that's not right. There's more numbers there. 3.95824, I think. Let's see if that was right. 98524, sorry. 98524. And so this is the x value where our pumpkin hits the ground. And so we don't want to know just what this is. We want to know the velocity, and that velocity we can find with our h prime of t. So h prime of t is negative 32t plus 60. I don't really have to write that down again. I found that on the last problem. So I'm looking for h prime of 3.98524. And so if I do negative 32 times that value, plus 60, I will get my answer here. So if we just type that in, negative 32 times 3.98524 plus 60, we are going to get negative 7,651.66. So negative 7,651.66. And this is feet per second. And so velocity, remember, has a direction. So that's why we have a negative here. At this point, the velocity is negative because the pumpkin's on its way back down. So its velocity would be negative for this problem. Okay, let's go to our next problem. The derivative of a to the x is going to be a to the x times natural log of x. So if we're looking for the derivative of, for number 4 here, I'm going to introduce a little bit new notation here. Whenever you have y equals instead of f of x, there are a couple ways that we can write this when we take the derivative. One is just to say that this is y prime. And so for this one, if we follow this pattern, we'd have 3 to the x times the natural log of 3. So that a right there is just your base. The other way that you could write this, instead of writing d, I'm going to write it like this, y equals a, 3 to the x. You're taking the derivative of this function, so d over dx, d over dx here. And so another way that we write this sometimes, if you think about this being over 1, that's not exactly mathematically correct, but it helps me remember how to write this. dy over dx would also equal 3 to the x times natural log of 3. So you can use either one of these types of notation whenever you're taking the derivative and you've got that y there. Let's look at the next problem. We're taking a derivative here, so f prime of x. 5 here is just a coefficient because this is 5 times 1.2 to the x power. So our 5 is a coefficient. It's just going to stick around out front here. And then our derivative of 1.2 to the x is 1.2 to the x times the natural log of 1.2. And so this would be our answer. Typically, you might see this written instead 5 natural log of 1.2 times 1.2 to the x, but it's really not a big deal if you don't write it that way. All right, let's look at our next problem. These are really the easiest right here. Exponentials are your easiest derivatives you can ever do as long as you remember what they are. So the derivative of e to the x is e to the x. E to the x is its own derivative. If you think about that rule that we just had, the derivative of a to the x equals a to the x times natural log of a, we can really use this rule for e to the x as well, because we would get e to the x times the natural log of e. But the natural log of e equals 1, so this is really just e to the x. So as far as exponentials go, you may see some of these where you have a base other than e, but the majority of the exponentials that you're going to see in this class are going to have e as their base. So whenever you take the derivative of number 6 here, it's so easy. 3e to the x, the derivative of that is 3e to the x. It is its own derivative. And then you take the derivative of 4x, and you're just going to get 4 there. So that's your derivative for number 6. For number 7, you have a little bit of a problem because you have this fraction here, but you have this negative exponent. And so when we have negative exponents, we can get rid of the negative exponents by moving that term to the other side of the fraction bar. So we could move this back up to the top and write this as 6e to the positive x. Now that was not taking a derivative, that was just rewriting the equation. So when I take the derivative, f prime of x, I'm going to just get 6e to the x because an exponential is its own derivative. Now for this problem, we're looking at the derivative of a log function with a base of b. And so whenever you take the derivative of a log function with the base of b, you'll have 1 over x times the natural log of b. So for example, here with this 8, I could use either the y prime notation, or I think I'll use the dy over dx notation here to indicate that I have taken the derivative. And I'll have 1 over whatever you're taking the log of, which is x, times the natural log of 5. So this would be my answer for number 8. For number 9, I'm taking the derivative, g prime of x. This 6 can sort of hang out front. It's just a coefficient. And then I'm going to have 1 over x times the natural log of 4. And so if I want to, I could put this back together. That's like 6 over 1. And so I could write it as 6 over x times the natural log of 4. Now, on this one, I just want to show you something crazy that the AP exam sometimes will do. If it is a free response question, please leave your answer like this. You do not have to simplify it further. But this is something they like to do on the AP exam. If you remember your rules of logarithms, 4 could be written as 2 squared. And our rules of logarithms tell us that we could take that 2 right there and move it out front, and this would be equal to 2 natural log of 2. And so a lot of times they'll do that for these problems, especially if it's multiple choice. Maybe this answer, 6 over x minus x times natural log of 4, won't be there. So they'll do this. They'll do 6 over x times 2 natural log of 2. And now this 6 and this 2 can reduce, and you'll get a 3 in the numerator. So you could also get 3 over x natural log of 2. And that could be an answer as well. On a free response question, please leave it right here. If it's multiple choice and you don't see this answer, it's possible that this answer right here could be what you're looking for. Alright, now let's look at a natural log. Remember, a natural log has a base of e. So really, we could think of that same rule that we were using for our other logarithms. It was log base b of x equals 1 over x times natural log of b. So if we do that for this, if we're taking the derivative excuse me, of natural log of x, remember that's like taking the derivative. We don't write it like this. It's not really correct, but it's like doing log base e of x. So that would be 1 over x times natural log of e. And natural log of e equals 1. So this is really just 1 over x. Now again, just like with the exponentials, you are much more likely to have a natural log than to have a log with a different base. So number 10 and 11 are going to show up a lot more often than numbers 8 and 9 will in your assignments. So if you're taking the derivative here for number 10, you're going to have 4 as a coefficient. It just hangs out front. The derivative of natural log of x is 1 over x. And so you just have 4 times 1 over x. This is like 4 over 1. So you're probably going to see the answer written as 4 over x. And then for 11, here our y prime would be, we've got a 6 times natural log of x. When we take the derivative of the natural log of x, we get 1 over x. So that's going to give us 6 over x. And then right here, I might should have rewritten before we took the derivative. This is x to the negative 2. So for this part, I'm just going to use that power rule. So negative 2 times this negative 1 right here is going to be positive 2 x to the negative 3. They may not leave the answer like this. They may write 2 over x to the third instead. Okay, so let's look at some of the equations, some of the questions that you might get. For number 12, it says write the equation of the line tangent to the graph of f of x equals 4x minus natural log of x at x equals 1. So when you're writing the equation of a tangent line, you need two things. You need a point on f of x and the slope. And so the point on f of x, this is going to be f of 1. And so we're just plugging 1 into our original equation. 4 times 1 minus natural log of 1. And the natural log of 1 is 0. So that's one that you want to make sure that you know. So you're just getting 4 right here. So that tells us that we're looking at the point 1, 4. That's our point on f of x. For our slope, we need the derivative of f of x because the slope is given by the derivative of the function. So f prime of x would be, in this case, the derivative of 4x is 4. And the derivative of natural log of x is 1 over x. So if we plug in 1, like we're asked to here, f prime of 1 is 4 minus 1 over 1, which is just going to give us 3. So this 3 right here is our slope. So remember to use that point slope form. If you've forgotten it, it's y equals m times x minus x1 plus y1. And so in this case, it's going to be y equals 3 times x minus 1 plus 4. So this would be your answer for your tangent line. Okay, let's look at one that's a little bit different. The line y equals mx plus b is tangent to the graph of g of x equals 3e to the x plus 2 at x equals 2. What are the values of m and b? So this one is going to ask us to find the tangent line, but they did ask for y equals mx plus b. So if it's asked in this particular manner, you are going to have to give your answer in y equals mx plus b form. It's just one extra little step. It's really not that difficult. It's very similar to the last problem. So we need a point here, so we're going to do g of 2 to get our point, which is going to be 3e squared plus 2. And if this is calculator inactive, we really don't know what that is, so we just have to leave this point as 2 3e squared plus 2. And then for our derivative, we would have g prime of x, which would give us 3e to the x, because the derivative of 3e to the x is 3e to the x. And the derivative of 2 is 0, so it's just going to go away here. So when we find g prime of 2, the slope here, we're going to have 3e squared. That's our slope. Now, if we use our point slope form, we're going to get y equals 3e squared times x minus 2 plus 3e squared plus 2. So I'm just plugging in those values just like I would if they were numbers like they were on the last problem. And now if I want this to be in y equals mx plus b form, I need to distribute my 3e squared. So I'm going to have 3e squared times x and minus 6e squared plus 3e squared plus 2. And so my m, my slope here, is the number in front of my x squared. I know that e looks like it is a, it's a variable, but e is a number. So if you go over here and type in 3e to the, let's see, green button, and then the x gets your e to the second power. I'm going to hit the green button before I hit enter. You're going to get a decimal. It's 22.1676. So, this would be calculator inactive. I was just wanting to show you that that is a number. So that's 3e squared. The b part is whatever's added right here. So the b would be negative 6e squared plus 3e squared plus 2. But I can combine that negative 6e squared and that 3e squared. So I would get negative 3e squared plus 2. It's also very likely that they would rather write it like this, 2 minus 3e squared, to avoid having that negative out front there. Okay. So even though these are sort of crazy numbers, they are our slope and our y-intercept for this equation. Okay, so for your assignment, you have several problems that you're going to do. You are going to look at page 143, 19 through 24, 35 through 38, and 49 through 52. And so for 19 through 24, those are just finding a derivative. You've got transcendental functions that you're going to be dealing with there. For 35 through 38, there you are getting the slope of a tangent line for those problems. And then for 49 through 52, you're just finding the derivative again. These are going to be a little bit more difficult than the ones that you have in 19 through 24. And then I want to add these three equations, or three questions right here as well, because our book does not put a lot of questions in there with natural logs and bases other than E. So I wanted to give you a couple more questions there, so please do these three questions also. You can take a picture of those and upload those on Canvas for your work.